Now that we know how to properly draw a Lewis structure, we can use these Lewis structures as flat pictures to make predictions about the three-dimensional geometry of molecules. The molecular shape of a molecule is important because sometimes it helps us to predict the reactivity of that molecule. When we work with bonding domains versus non-bonding domains, a bonding domain can be a single atom that is connected to the central atom, so something like a singly bonded fluorine. Even if we have a double bond, it still counts as one bonding domain. It takes up a lot of physical space because it's actually an atom. Non-bonding domains, on the other hand, are just pairs of electrons that are connected to the central atom, and they do take up a little bit of space, but not nearly as much as an atom. Electron pairs, both bonding domains and in non-bonding domains, repel each other. The most energetically favorable conformation is the one that reduces the amount of electron repulsion. That's a fancy way of saying that domains separate in a geometry so as to get as far away from each other as possible to reduce the electron-electron repulsion. It lowers the overall potential energy of the system. This is a linear molecule. I drag it every which way, but those two atoms that are sticking off on either side are going to keep orienting themselves in a 180 degree bond angle to be as far away from each other as possible. The best arrangement of electron domains is one that minimizes electron-electron repulsion. Valence shell electron pair repulsion theory. A term that is slightly different than bonding domains versus non-bonding domains is the electron pair geometry, or the electron domain geometry. It's simply just the geometry that corresponds to the total number of domains. When we look at NH3, which is ammonia, we know that ammonia has 3 bonding domains and 1 non-bonding domain, but if we count the total number of domains is 4. So we say that its electron domain geometry is tetrahedral. However, we know that its molecular geometry is trigonal pyramidal because we ignore the essentially massless electrons when we come down to actual molecular shape. Molecular geometry is taking our electron pair geometry, and like I said earlier, ignoring that pair of electrons, which then gives us the actual shape of the molecule. Those pairs of electrons still have an effect on the molecular shape, though. They repel the other domains, and that's why, even though that we consider it not a part of the molecular geometry, it still influences the overall shape of the molecule. One single electron domain base geometry can have several subgeometries that are molecular geometries. If you have 4 total domains, the electron pair geometry is always tetrahedral. However, if 3 of those domains are bonding, it's trigonal pyramidal, and 2 bonding domains out of the 4 makes it bent. So you can have several molecular geometries that share the same overall electron domain geometry. The linear domain is the easiest to describe. 2 bonding domains, 0 non-bonding domains. The easiest way for those atoms that are on the sides to get away from each other is to form a linear shape. Linear molecules have a 180 degree bond angle, and that is the simplest geometry that exists. One other thing to note is that all diatomic molecules that are composed of only two atoms are linear. It's the simplest shape that you can make with 2 points. Trigonal planar electron geometry is when we have 3 bonding domains. If we have 3 total electron domain geometries, 3 total electron domains, there are 2 possible sub-geometries that we can have, trigonal planar and bent. 3 total domains are going to orient themselves in a 360-degree circle. However, the shape of the molecule is going to look triangular, trigonal planar. If I take one of those bonding domains and add an electron pair to that electron pair is still going to push on these atoms. And actually, this bond angle that's being represented in this program is not 100% accurate. Electron pairs take up more space and they have increased electron-electron repulsion because they don't have a nucleus attracting them. Therefore, this bond angle would be predicted to be a little bit less than 120 degrees. Non-bonding domains are larger. They create more electron-electron repulsion within a molecule. Like I explained earlier, without that extra nucleus to rein in those electrons, they occupy more space and they actually do a better job at repelling. For each electron pair that you add, it constricts and shortens the bond angle by pushing on the bonding domains. Another topic that we didn't cover in sophomore chemistry is the effect that double bonds technically have on bond angles. You would look at these domains and you would say, well, this is trigonal planar geometry, and that's correct. However, because of the extra electron density of those pi bonds, those p orbitals that have overlapped, because there's a little bit more electron density on the one side, it actually does constrict the bond angle on the opposite side of the molecule. If we have 4 total domains in our electron domain geometry, there are 3 sub-molecular geometries contained within that arrangement. If I have four total things attached, we end up with a tetrahedral arrangement with 109.5 degree bond angles. I take an electron pair away, I take a bonding domain away, and I add a lone pair instead, I get trigonal pyramidal. This bond angle should be a little bit less, closer to 107. I can do that again, and I end up with a bent geometry, less than 109.5, closer to about 105 degrees. And those are the subdomains contained within tetrahedral arrangements. Then we start to get into the more complicated shapes. Trigonal bipyramidal is 5 bonding domains. 1, 2, 3, 4, 5. There are 2 positions oriented in a straight line called our axial positions because it forms an axis. This axis forms a 90-degree angle with a flat triangle. And this flat triangle has bond angles of exactly 120 degrees going around in a circle. When we put electron pairs into this electron domain conformation, we put electron pairs in the triangle. Why is that? Well, because the bond angle of the triangle is 120 degrees, and the bond angle between the axis and the triangle is 90 degrees, it gives the electrons more room. It decreases the electron-electron repulsion if we put electron pairs, if needed, in that triangular equatorial position. So for instance, if we have sulfur tetrafluoride, the lone pair of electrons that's added would actually go into that triangle, so we're missing one of the sides of the triangle, which therefore has an influence on the overall shape of the molecule. The trigonal bipyramidal arrangements has 5 total domains sticking in different directions. We can replace one of those domains with pairs of electrons to get different shapes. Starting with our base arrangement, which is 5 bonding domains, trigonal bipyramidal. Take a bonding pair off, add a lone pair. Now, it kind of looks like a seesaw. Why does it look like a seesaw? Rock it back and forth. Here's my seesaw, and here's the axis that it would bounce back and forth on. This is called a seesaw arrangement. It has 1 pair of electron in the triangle. If I have 2 pairs of electrons in the triangle, it makes my molecule T-shaped. These pairs of electrons are actually pushing on the molecule, so I would expect these bond angles to be a little bit less than 90 degrees. I do that one more time, and I show just the atoms. I'm back down to linear. So if I actually have 2 bonding domains and 3 non-bonding domains, it gives us a linear geometry when it comes to the actual atoms. The octahedral electron domain has 6 total domains. Within those 6 total domains, we have 3 different sub-molecular geometries. Square pyramidal is included as well, and square planar. And if we go in to this simulation, take away our electron pairs, 1, 2, 3, 4, 5, 6. It doesn't matter which way I rotate this, it's all the same in the same direction. All of these bond angles are 90 degrees. This is octahedral arrangement. If I take one of those bonding domains and add an electron pair, rotate it a little bit, take that electron pair away, it becomes a square pyramid, square pyramidal. Do the same thing, take one bonding pair away, add another non-bonding domain, hide them to show the massive atoms, and I end up with square planar bond angles of 90 degrees. We're going to do a few practice problems involving molecular geometry after you've concluded this video.